This lecture will cover Chapter 2 of the textbook and is titled Sampling Design. So most universities have a whole entire course devoted just to the subject of sampling design. And of course, this particular course, Elementary Statistics, is really a survey of all these different aspects of statistics. You're required to read the whole chapter, but this lecture is going to focus on the main ideas from Chapter 2. But I do strongly encourage you to read the chapter and look at some of the other aspects, and I'll get into that more as we go through the lecture. So as we begin to think about sampling design, the first thing we need to do is clearly understand some of these definitions. The population is the entire group of objects or individuals under study about which information is wanted. And a unit is an individual object or person in the population. And then we call the units subjects if the population consists of people. So a sample is a part of the population that's actually being used to get information. And a variable is a characteristic of interest to be measured for each unit in the sample. The size of the population is denoted by the capital letter N, and the size of the sample is denoted by the small letter lowercase n. Here's a Venn diagram that gives a sort of overview of how this idea is going to work. Now, the large ellipse here is illustrating or representing the entire population. So each member of the population is a unit, and if the unit turns out to be people, then we call those units subjects. So in this particular example, there are 16 objects in the population, and we're going to be taking a sample of size 4. And so this smaller group from the population is what we would call the sample. A parameter is a numerical value that would be calculated using all of the values of the units in the population. A statistic is a numerical value that is calculated using all of the values of the units in a sample. Now here's a tip. One way to remember this distinction is the letter P is for population and parameter, while the letter S is for statistic and sample. Now, the really important idea here, or a really important idea, is that since the parameter is calculated based on the entire population, we assume that the parameter is constant and not changing. And of course, this is not always a reasonable assumption if the variable of interest, or I should say the parameter of interest, is likely to change. Or, sometimes the parameter value could be constantly changing. But when we do statistics, we can't really think about it like that. So one of our simplifying assumptions is to assume that the parameter is constant. And sometimes we think about this as, in terms of doing statistics, that really we're taking a snapshot in time. So the way to think about this idea is when we go and we do our sampling, the results we get from the sample and the inferences we make about the parameter are really relevant for that time period where the data was collected, or when the data was collected. And it's certainly quite possible that, days, months, years down the road, that the parameter value could have changed. And so the statistical analysis is really, again, we should think about it as a snapshot in time when we do our calculations. Now, and that's the parameter. Now, so we assume the parameter is fixed. We're always going to assume the parameter value is fixed, okay? But then on the other hand, since the statistic is based on a sample from that population, and since different samples could result in different statistic values, we consider the statistic to be a variable. And the idea is confusing, and I understand that, but really what you have to understand is both these things can't be changing at the same time. That would be very problematic. So we assume the parameter is fixed, and generally that is a reasonable assumption to make, especially if we think of our study as being a snapshot in time. But the statistic has to be a variable, and it is always a variable. And again, there are different statistics that we're going to be studying. And the other thing that I think is important to realize is that every parameter has a corresponding statistic. And I'm going to do an example here in a little bit and illustrate this idea. Here's some more definitions. A sampling method is biased if it produces results that systematically differ from the truth about the population. A convenience sample is a sample consisting of units of the population that are easily accessible. A volunteer sample is a sample consisting of units of the population that choose to respond. Convenience samples and volunteer samples are generally biased. Here are some specific types of biases. Selection bias is the systematic tendency on the part of the sampling procedure to exclude or include a certain type of unit. Non-response bias is the distortion that can arise because a large number of units selected for the sample do not respond or refuse to respond. And these non-responders have a tendency to be different than the responders. Response bias is the distortion that can arise because the wording of a question and the behavior of the interviewer can affect the responses received. So let me talk a little bit about these different types of biases. Now, bias is really a problem in statistics. Bias is really something that can really have a profound effect on our results. If our mathematics can be, perfect and done exactly correct, but if the sample we're basing all of these statistics on was collected in a way that resulted in some kind of bias, then all of our results we were completely misled by the results of our study. So for example, one type of sampling design that's used often by people who are doing surveys of people is called it's something called an intercept survey. And this is where you might have been approached perhaps in a store or some kind of a chain store or something at some point by somebody with like a clipboard, and they have a whole series of questions that they want to ask. And these intercept surveys are often subject to this idea of selection bias. And really, the people doing the survey need to be extremely well trained, because the problem is humans are biased. We are all biased. And so, and you can even imagine, if you were in this job where your job was to go and talk to people and try to convince them that they need to do the survey, you can probably imagine in your own mind, if you were doing this, that if you're honest with yourself, perhaps you would think, yeah, there are certain types of people that maybe I wouldn't really want to talk to, and there are certain types of people that I would maybe gravitate toward more. And, to make matters even worse, if like your supervisor had like quotas for the number of surveys that you were required to get in a day or something, then probably, and I can totally imagine myself doing this, especially before I understood statistics so well, where, I would be like, well, it seems like people that, are dressed a certain way are more likely to answer my survey, and so I'm going to kind of like find those people. And so even subconsciously, whether we even think about it or not, I think subconsciously we would, some of us at least, maybe would have a tendency to gravitate towards certain um, personality types, or all these different things. So again, this is an example of selection bias. And what it would be is, the procedure is excluding or it's including a certain type of unit. In this case, in my example, it would be a subject. The other kind of bias we can get is what's called a non-response bias, and this is where this happens a lot in volunteer samples, where people are solicited to respond, and there's no necessarily there's not necessarily any kind of follow-up to ensure that the entire group identified, say, to be sampled is actually included in the sample. And a lot of times when, well, I'll give you an example. I don't know if you listen to talk radio, but if you listen to KINS, the local talk show on AM dial in our area, in Humboldt County, in Eureka area, there's the question of the day, which is like this phone-in kind of survey they do. And, this is an example of a volunteer sample, because certainly it's the people that are going to be sampled are the people that are listening to the radio show, people that are interested in talk radio. And, and that's not necessarily where the non-response bias is coming in. Well, it is partially, I guess, because if you're not, if you're not listening to the radio on that day, or if you don't listen to talk radio, then you're not able to participate. But also, if you're also, the other thing to keep in mind is that the people that tend to voice an opinion on a particular subject are often people who have a strong feeling about it one way or another, and therefore they're more motivated, say, to participate. And so volunteer samples very often result in non-response bias. And so, I don't know, I mean, if there's some controversial issue out there, people perhaps that are strongly opposed are going to call in and voice their opinion more, or are more likely to do that than people who, are moderate or in the middle of the road and don't really have strong feelings and aren't really willing to take the time out of their day to make the phone call or what have you. So that's kind of an example of a non-response bias. And response bias is again yet another kind of bias, and this type of bias can be due to the wording of a question or how the question's asked. So, as an example, if I'm interested in learning about, say, the cigarette smoking behaviors of a certain population, and I identify a sample, and I go and I start talking to the people, contacting the people, say the subjects for my sample, and I ask the question like this: you don't smoke, do you? Do you think that I would have that I could potentially bias the response? Do you think that it's possible that some people, even if they smoked, or even if they smoked occasionally, if I phrased it this way, you don't smoke, do you? Might say no? Maybe, it doesn't really matter whether or not that's true or not. The problem is, even if there's a possibility that that's true, it would bias, it would taint the credibility of the study. Here's an example. Here's a let's do it right out of the textbook to kind of, again, look at these different terms and definitions. So a study was conducted to estimate the average size of households in the United States. A total of 1,000 people were randomly selected from the population, and they were asked to report the number of people in their household. The average of these 1,000 responses was found to be 4.6. So here are our questions. What's the population of interest? Households in the U.S. What is the variable of interest? Number of people in a household. What is the parameter of interest? Oops. So the parameter of interest is the average number of people for the entire population. And the only way we could calculate the parameter is if we could actually sample all the households in the entire population in the United States. So in other words, this is a great example of why the parameter is something that we have to believe exists, but we really have no ability to calculate. Because how could anyone ever sample all households in the United States? And actually, the U.S. government does attempt to do this every 10 years. And it's called the U.S. Census. And of course, when we sample an entire population, we call that a census. But our government is really never able to accomplish that goal. And it's really unachievable. There are so many households in the United States that it's virtually impossible to know even that you've sampled every single household. Households fall through the cracks and they are not ever sampled. It's just a reality. Let's take a look at Part D. I think Part D of this example really exemplifies the kinds of pitfalls that we can have when we're trying to sample in statistics. So here's the question, or here's the an average computed in this manner would tend to be larger than the true average size of households in the United States. Explain why this would be the case. So why would this sampling method tend to inflate our estimate of the true average size? Well, here's why. Let's look at a couple of households. Let's say household 1 as one person. This is just a single person living alone, and they constitute a household. Let's say household 2 has 2 people in it. And let's say household 3 has 4 people. And just for the fun of it, just to kind of exemplify this situation and the problem here, let's just say these 3 households, let's just say these 3 households constitute our population. Well, since we're sampling the people, right, and you know, if I like put the people, if I gave the people numbers or something and said, okay, I'm going to randomly select you know, 2 numbers, whatever, and then those households will be part of my sample. Well, the problem is, since household 1 only has a single person, and since we're sampling people, household 2 has twice the chance of being selected as household 3 because there are 2 people in household 2. So there are 2 people in household 2, so the chance of this household being selected is twice as great as the chance of household 1. And household 3 has 4 people, so it's 4 times more likely household 3 is sampled than household 1. And what that means is, if our sampling design is to sample people and then inquire about how big their household is, clearly the larger households are going to have are going to have a greater likelihood of being included in the sample. And so that's going to inflate the estimate of the true average. So a better way to estimate the average size would be to sample households rather than individual people. So again, when we are doing our sampling, when we're designing our sampling, or think about our sampling design, we have to really think about what is our variable and what sampling methodology is going to give us the most representative sample. Now here's a really important idea. A sampling method that gives each unit in the population a known non-zero chance of being selected is called a probability sampling method. And there are a good number of different probability sampling methods. And actually, we can even use our imagination and create a lot of different types of probability sampling methods. But the real idea here is that when we use probability as part of our sampling procedure, what it does is it removes the human element from it. Because, again, humans just basically are incapable of doing random things. So when we create a sampling method that involves some kind of probability method, it removes the decision process from the researcher and places it in the realm of chance. And mathematically, then, the chance of a bias in the sample is much lower. Now, there are many ways to sample, and I'm not going to go through each and every one of these ways, and these are all explained very well in the textbook. Simple random sampling is kind of the gold standard of sampling, I guess, if you will. I mean, when it's possible, giving every member of the population the same chance of being included in the sample is really the best case scenario. But that's not always possible, and that's why we have these other types. And, you know, honestly, it's possible that a simple random sample in certain circumstances may not even be the best way to sample. But again, like I said, you know, really to thoroughly learn about all these different sampling methods, I think requires a lot more time than we really have in this course. So I'm just going to, again, stick to the main ideas. here's another example I want to look at, and this example I want to demonstrate a couple of different ideas here. One of which is the idea that a statistic is a variable and a parameter is fixed. And what I have here is just a table of representing a class of 36 students, and I have all the ages of the students here. And what I'm going to do is two things. First of all, since I have all of the population here, if I think of the class as the population, if I'm interested in the average age of the students, then I can actually calculate the parameter here. Okay, so the parameter, and again, what we're going to calculate here is what's called the mean average, and the mean average is really covered in Chapter 5 of the textbook. But I know many people have calculated means and have a basic idea of what the mean is. So I'm going to go ahead and use this as an example to illustrate this point. So what I'm going to do, all right, hold on now, I got to remember here, hold on. I got to do this a different way. Okay. There we go. So what I'm going to do here is I'm going to go ahead and enter this data into the calculator, or the ages for the students in this class, and then I'm going to calculate the average. So part of this is kind of giving you a first example again on some things that on how to use the calculator. So I'm going to go ahead and go to Stat, and I'm going to go to the data editor, and I'm going to go ahead and use L1, and it honestly doesn't really matter which list you use. And notice I have some values, some data in L1 left over from a previous example, so I need to clear this out first thing. So to clear a list of data, all I need to do is, again, move my cursor all the way up to the top. Make sure you've got the top L1 is selected. And again, I want to point out, I know I've talked about this in a previous lecture, but notice how the calculator is using the braces here, and it's actually using set notation. And if I scroll down here into the body of the list, then notice that we have the parenthesis with a 1 here, indicating the first element in list 1, and then it's just a single number with no set notation. And so when we're within the table or list itself, what we're doing is we're talking about individual data values, and when I move the cursor all the way up to the top, then I've selected the entire list or the entire set of data. And essentially what I want to do here is clear the data out so I can put this new data in. And notice that when I press clear, it erases the data on this formula bar down here, or the set down here, but it's still data inside the list. And if I accidentally hit clear and I didn't mean to, I could save it right now by, or recover from this now by going second, quit, which takes me right out of the editor back to the home screen. And when I go back to the editor, notice that that data is still there. So I didn't actually clear all the data out by doing that. If, though, I move my cursor all the way to the top, press clear, and then press enter, now the data is gone. And I can enter the new data. Let's see, I've messed up here. Let me get this. let me get this right. All right, so this will give you plenty of time to enter the data as I figure this out. So, so let's see. Subject 15 is 21. All right. I struggled a little bit for some reason entering the data. So sometimes what I do is if I want to double check that I entered the data set correctly, I actually go from the bottom back to the top. And I'm just going to do that real quick to double check, make sure that I don't have any mistakes here. All right, looks good. Okay, so what I'm going to do now is I'm going to calculate the mean of this data set. And one of the ways, now, all right, so one of the ways we can calculate the mean is to, and actually I'm going to do this a different way. So I'm going to go second stat instead, and this actually takes me, if you look above the stat key, you see list. This takes me to the list menu on the calculator where I can see all the lists that I have defined in the calculator. I can do different types of list operations, and when we entered the bags program, we were here, using the dim feature and things like that. And then there's also a math feature, and notice under the math feature it gives me an option to calculate the mean. So I select mean and I put it in the wrong place. Hold on a second now. This is one of the areas where I want to do second quit because I just made a mistake here. So I want to go second quit. Now what should have happened when I go back in and look at that list is it's the same. It didn't get affected because again I started to do something within the list editor. I didn't realize I just again made an error. Had my cursor in the wrong place when I went to look for the mean function. So what I'm going to do now though is second quit to come out of the editor now, and then I'll go second stat over to math and I'll choose number 3 for mean. And what I want to find is the mean of list L1. I'll press enter. So the true average age for this class of students is about 23.7 years. All right, so the parameter value is 23.7 years, okay? Now, what I'm going to do is I'm going to go back to the calculator again, and all right. I'm going to go back to the calculator again, and I'm going to select a random sample. Now, I want you to follow along with me, okay? And what we're going to do is we're going to just type 5. Everybody type 5. Press store. Go to math. Go to PRB and select number 1, rand, and then press enter. And I know, you may be wondering, well, why in the world am I doing this? And I'll reveal that to you a little bit later. So I want to talk about a way that we could actually do some random sampling here. And since all of the students over here have their numeric label, if I have a random way of selecting these numbers, then I can use that to, again, select a random sample. So the calculator has several random number generators built in, and one of them is called randint. And what randint does is it randomly selects values from the set of integers starting from the smallest in the what we could think of as the domain, or the sample space, or the set of possible numbers. So since my students are labeled 1 through 36, what I'm going to do on the calculator is select random integers between 1 and 36, including 1 and 36, and that's what random does. And it does it based on a uniform distribution, which means it's going to sample these numbers with equal probability. So I pressed enter. So student number 27 is included in my sample. I'll do that 5 more times. So student 27, student 11, student 5. Let's see, 27, 11, and 5. Now, the thing to keep in mind, though, is even though even though these are my random numbers, 27, for example, isn't the data value. The student that's labeled 27 is 18 years old, so that's my actual data value. And then I look for the student that's labeled 11, and that student's 22, so that's the actual data value, other data value. Student number 5 is 16, so that's another data value. And then if I say I'm going to select 5 students, then maybe I'll select 2 more, and student 13 is included. Student 13 is 20, and student 16 is included, and that student's 25. So what I can do now is calculate the mean of the sample. Now, before I do that, okay, I'll do that in a minute. I want to acknowledge that if you actually did that previous step where you stored 5 into rand, what you are seeing is your calculator has selected the exact same 5 random numbers mine did. And what that indicates is that what's going on in the calculator doesn't seem like it's truly random. And it isn't truly random. As a matter of fact, no electronic device, no computer is capable of random sampling, of randomness. And the reason is because a random process is completely unpredictable. The thing about computers and calculators is that they are computers. They are based on programs and what in mathematics we call algorithms. And therefore, if you know the input value, you can predict the random sequence. And the process we just went through where we stored 5 into rand, the process is called seeding the random number generator, and 5 is called the seed value. So if you know the seed value for a random number generator on a computer, then you can predict the random sequence. But it turns out it doesn't really matter as long as the seed value is unknown. So in other words, if we, even though it's possible we could predict the sequence, as long as we don't try to do that, or we say, and in some instances, the seed value is some other type of random number that's out there. Like, sometimes, statisticians will use like, I don't know, the day of the year, maybe, or the seconds on their watch as a seed value, or something like that. Just something that, they're not really cognizant of, and as long as there's not an intention to manipulate the random number sequence, the pseudo number generators we use on computers work very, very well. And generally, statisticians would consider that to be a random sample. So in any case, now that we've gotten that out of the way, let's go ahead and calculate the mean here. And one way I can do this is just to go to Second Stat Math and choose number 3. And I believe, if I remember right, if I put braces here, notice I went second function parenthesis, and what's above that is the brace. Then I'm going to type in 18, comma, 22, comma, 16, comma, 20, comma, 25. Close the brace. Whoops, hold on now. Okay, second function parenthesis, then close parenthesis. So the average is 20.2. Now, if you recall, the average of the whole class was 23.7, so 20.2 is different. And that's important to recognize. Now what I want to do is collect another random sample from this class of size 5 and see what happens. So now here's a shortcut on the calculator that's useful. If I use second enter, the calculator brings back the previous command. And if I press second enter again, it brings back the one before the most recent, the last one. And again, if I go, so essentially what I can do is go down through the, I believe that you can go 10 deep into what we call the stack of commands on the calculator, and re-execute those commands. So again, in this example, oh, and then the other thing is I can modify that command. So if I add a 5 here at the end and press enter, the calculator will find all 5 random numbers at the same time, which is, convenient. So now what I'm going to do is, again, I'm going to go second enter, and I bring back random int, and I go second enter again, and it brings back the mean average calculation here for the sample. And what I'm going to do now is I'm going to replace these values with the new data value. So what I'm going to do is go to student 16, who's 25 years old, and I'll modify that data value. Student 15 is 21, so I'll change that age. Student number 4 is 32, so I'll change that age. Student number 23 is 18, so change that age. And finally, student number 12 is 35 years old, so we'll change that age. And then when I press enter and calculate the mean, notice I get yet again another value for the sample mean. So notice that this is the idea. So the parameter value isn't changing because the students if I average all the students in the whole population, I get a fixed number. But if I go in and randomly select them 5 at a time, each of those sample means is going to be a different value. And so the statistic is the sample mean. The parameter is the mean of the whole class. So notice how the sample mean is changing or varying from one sample to the next. And so again, the statistic is a variable and the parameter is fixed. All right, well, that's it for this lecture, and I'll see you next time.